we are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about the properties of the nanomaterials that we prepared by considering various methods. So, in our previous class we have discussed few methods, heat transfer and other properties. So, today we will discuss basically mass transfer, that is one of the main chemical engineering unit operations process. So, there are also many applications are there. So, here nanomaterials that can be applicable. So, with that defects also, that is also another things we will discuss. So, today's contents are properties of the nanomaterial. So, out of that today we will discuss basically mass transfer and defects in crystalline material. So, these are the two things we will discuss today. Also the chemical properties of the nanomaterials, few components we will discuss in this lectures. So, let us start the mass transfer and nanoparticles or nanofluids. In mass transfer, I said it is a unit operations, one of the chemical engineering unit operations like heat transfer. So, nowadays if you see that due to the use of fossil fuels, the generation of CO2, that is the greenhouse gas that emitting to the environment or atmosphere, that gradually day by day it is increasing. So, if you notice, it was 1980 it was 340 ppm in the CO2 level in atmospheres, and currently or 2019 it is 408 ppm. So, that has gradually increasing. So, once whenever in any particular process, let us say combustions or in petroleum industry where CO2 generation is there, or thermal power plants where CO2 is generated, that is as a greenhouse gas, that we can directly trap or we can separate out from the flue gas or other combustible gases from where CO2 is present. So, for that means there are mass transfer operations equipments are available, many equipments are available. So, using that we can separate out the flue gas, the CO2 from the flue gas, means whatever the concentration is present when it is generated, after that we can remove, or before dispose to the environment we can take out that those CO2 by different process. So, means direct captures we can do, or utilizations, or we can say CCUS process we can separate out by using any solvent. So, mostly water, that is the basic solvent that is used, but with that once we use nanoparticles in that particular solvent, so then the property of the solvents, that is we can say nanofluids, will different. So, as a result what would happens, the CO2 captures or separation of the CO2 from that gas would enhance or increase. Okay, so by using a particular equipment. So, here we using nanomaterials, nanoplates or MOP type of composite, we can separate out the CO2 by CO2 absorption process. Okay. So, here various nanomaterials that we, or nanoparticles that we have discussed in our previous class also. So, addition of nanoparticles, so what would have effect, or what would increase mass transfer coefficients, that is KL by Kg. So, that will increase. So, as a result increase that mass transfer coefficient, convective mass transfer, that will, or mass transfer, that is the Na, that is called flux, that will increase. So, here mass transfer we can say that diffusive mass transfer or convective mass transfer. So, in both the way, means one is molecular phenomenon. So, when there is a concentration gradient in a mixture, so that diffusion coefficients of mass transfer that we can measure, or that also would affect based on the particles or nanoparticles we are using in a particular separations process. Similarly, when the system is a flow system, so then convective mass transfer operation is there. So, then that convective mass transfer process, that would be influenced with the help of nanoparticles or nanofluids that we are going to use. So, that would changes the separation characteristics of or mass transfer properties of that particular system. So, here few systems we will discuss. So, falling film absorption systems where CO2 will be separated out using nanofluids, then tray column absorption systems where CO2 will be separated out with the use of nanofluids, and another is gas liquid flow hollow fiber membrane systems where also CO2 would be separated out from a multiple or two different gas mixtures. CO2 is present, that can be separated out. So, here just basic things we can use or we can discuss. So apart from that, there are some others also mass transfer operations are there. So where CO2 oxygen instead of CO2, other component also can be separated out. So that I'm not going to discuss, only based on this we'll discuss. So here's one is falling film absorption system. So where CO2 would be separated out by using MDA, methyl diethanol amine solutions, solutions that would be used to separate it out that CO2 from the gas mixture where CO2 concentration is higher. So if you want to down that CO2 concentration, so means this type of absorption systems is used to separate out. See here one concentrated solutions, liquid films, that would be concentrated solutions in the form of films that would be come down from the columns, and that would coming out from here, and then one cooling water inlet, cooling water outlet systems is there, and then the components present in the vapor, so that would be will pass and they will come in contact with the liquid films, and then the CO2 having higher concentration that would be absorbed in the solvent, and by that way we can get reach to the lean or dilute or gas components that mixtures present CO2 higher concentrations. We can separate out CO2 from that gas mixtures by using that solvent. So here in this particular way, if we use some nanomaterials, so it has been observed that it would increase the mass transfer coefficient. So 92.8% increase when we use magnetic nanoparticles, iron oxide, ferrosylfuric oxide, that kind of nanoparticles. If you are able to prepare and use that materials with that solvents, very small amount, 0.39 weight%. So then it has been observed that the mass transfer coefficient increased 92.8% or 3 approximate 3%, 90% percentage efficiency will increase. Similar to the another column, tray column absorption tower systems is there. So where is also we can use nanoparticles to separate it out CO2 by using tray absorption columns. So where liquid will be, nanofluids will be passed through these columns, and another component that we need to separate out, that is CO2. So in these tray columns where is called absorbers, here if we add 0.0505 volume percents of the nanoparticles with that solvents, means in here's silica nanoparticles or aluminum nanoparticles, either ones we can use in methanols, that is the solvents, and the concentration of the nanoparticles may be very less quantity, 0.005 to 0.18%. So then it has been observed that so enhancements of absorption rate of CO2 in case of aluminum nanoparticles whenever we are using, so 9.4% absorption rate is increased or enhanced, and when silica nanoparticles are using in that solvents for separations out CO2 by using this tray column, tray absorption tower, so then the absorption efficiency has been increased 9.7%. So then this is second example. Another one is the gas liquid hollow fiber membranes contactor systems, where is also suppose we have a CO2 nitrogen gas mixtures. So if you want to separate out CO2 from that mixture, so then this kind of porous membranes we can use, and with that membranes we can use some nanoparticles. So then that would enhance the separations of CO2 from this nanofiber or this type of gas liquid conductors. So where solvent will pass from the top to upper directions, and this means liquid will absorbance will in here and out here, and the gas having CO2 concentration side that would be passed through the outside. So then they are using some nanoparticles. So conventional efficiency, the separation of the CO2 from that gas mixture by using conventional membranes. So the efficiency whatever we get, and once we use some nanoparticles, here's one example, 0.25 weight% of graphene oxide nanoseeds that was used with the polysulfones hollow fiber mixed matrix membrane. So with these membranes, if we use 0.28% of graphene oxides and then design that membranes if you used for this type of gas liquid hollow fiber membrane conductor systems, so then it has been observed that the separation efficiency of the CO2 that is increased 201% increase than the conventional membrane. So here you can see this is conventional membrane. So where this is the CO2 and methane gas mixtures are there, so that would be passed through these membranes. So the separation efficiency is schematically shown here, and here so when the same CO2 and carbon dioxide, CO2 and methane mixtures are there, that would pass through these modified membranes, that is modified with graphene oxide. So this is graphene oxide and this is membranes, HF membranes, fiber mixed matrix membranes. So here this is CO2, the it would pass through these membranes and are separated out from that mixture. So it has been observed that separations efficiency 201% higher than conventional membranes. So here we usually the mass flux usually express any average. So this is flux of components that is separated out, and here clearly that is the mass transfer coefficient. This is the concentration driving force. So initial and final concentration or concentration driving force in between two different state or two different locations where the concentrations here are CO2 means that may be a CO2, R means C means RO2, that is equals to CO2. Okay. So if R is changes into S, that would be SO2. Okay. So depending upon R is just to either it can be applied for CO2 separations or SO2 separations. So it has been was observed that if now conventional solvent if we used water, then mass transfer coefficient, that is KL, is 1.03, that much. So whence with that waters if we add some SO2 or 2O3 or alumina nanoparticles, so base fluid has been changed into SiO2 water or Fe2O3 or alumina. So then it has been observed that you can see that mass transfer coefficient gradually increase depending upon that nanoparticles we are using with the base fluid to make that solvent that can be used for the separations of the CO2 from the CO2 rich gas. So here, so this is the nanoparticle has a roles to separate it out, that any target component means gas component, that is CO2, SO2 whatever. So depending upon that gas mixtures we have that rich gas, we can separate it out by using various nanoparticles with the solvents. Here also a CO2 absorptions enhancements by using various nanoparticles that has been shown. So here's alumina, CNT, Fe3O4, multi-on CNT, SiO2, TiO2, a very small fractions of that nanoparticles we can use with the base fluids to make a nano fluids, and that we can use as a solvent for separations or CO2 absorption. So it has been reported that, so there is some enhancements of the efficiency or performance of that using nanoparticles. Okay. So now chemical properties we want to discuss. So chemical property means nanoparticles, whatever the metal oxide, carbon based, ceramic based, whatever the materials we are using or we are synthesizing, it has chemical properties as well also. That materials we can use particularly increase the stability, sensitivity, toxicity, corrosive and anti-corrosive, oxidations, reductions properties, antifungal, antibacterial and disinfection. Means that materials whatever we will prepare metal oxides or other materials, so that has some chemical property also depending upon our application. So we can use those chemical properties to separate or for particular applications we can use that. So now here it has been one or two example just want to show. So where it has been observed that if you want to remove this type of atrazines, that is pesticides that spray into the agriculture or forest or domestic uses. So they are using SiO2 nanoparticles, we can separate it out or we can remove that particular pesticides very easily. Even iron oxide nanoparticles if you use for a particular wastewater treatment, so where many virus or other components are present, so bacterial this present, so we can separate it out using this means nanoparticles, we can easily remove those components. So that particular nanoparticles has a some property, so that would help to chemical property that would to separate out or to kill those virus or bacteria from that particular wastewater or others, groundwater or drink water whatever. So there if it is present small amount, so that easily we can separate out or we can reduce those components present in that particular waters or whatever. Depending upon the size of the nanomaterials, they also will affect. So if we prepared 100 nanometer size of nanomaterials and 10 nanometer, 20 nanometer, any size of we can vary, and depending upon their activity or chemical property also will affect. Okay. So now defect in crystalline materials. So whatever the materials we prepared, that may be crystalline materials, that may be bulk or maybe in a nano phase. So if we have a crystalline materials, so in crystalline materials has many defects may be there. So various type of defects that we will discuss. And if we prepare that material from bulk crystalline to nanocrystallines, means if we do the size reductions, means this is bulk materials to nanomaterials. So then there, if some properties, means defects are present in crystalline bulk crystalline materials, if we reduce that size or size reduction, so then this type of defects, many defects are present, so that we can eliminate. Okay. So defects, since in bulk materials many defects are present, so that defects, yeah, if we means depending upon in materials there are different type of grains are present, or grains, small grains, larger grains, different size of grains are present. If we are able to decrease the grain size, so then that dislocation stability, that is we can reduce or we can lower down that. Okay. So in nanocrystalline materials, effect of grain size. So grain size, depending upon the grain size, their physical properties or mechanical properties. The physical properties are this and mechanical properties are this. These are the will change. Means when a materials that we prepared in crystalline material, bulk crystallines, if that convert into nano, so many defects I said, depending upon their grain size, if we reduce, then that property will change. Okay. So physical property, mechanical property, that will change. In crystalline materials, what are the different type of, means defects are present, that will discussed. And then it is point defects, line defects, surface defects or volume defects, various type of defects are present. So any kind of disruptions in that materials or crystalline materials, so that is called crystalline defects. So that may be 0D, 1D, 2D or 3D, depending upon that materials and preparations. So these are the various type of defects are present, and we can eliminate those defects by converting that crystalline material into nanocrystalline materials. So point defects, that basically present in metals and alloy, so that is vacancies and substitutional interstitial solutes, that is very common. So even point defects, that is cascade defects and Frankel defects are called. So in cascade defect, here anion cations, both type of ions, positive and negative ions, that both are absent, and in Frankel's here only a particular same type of ions, either it is positive or cations or anions, whichever, that is absent. So that type of defects are present, that is called point defects. And line defects, a particular missing of planes of the arrangements of atoms or planes of atoms. So that absent or dislocations is there in type of particular crystalline material. Even surface defects, that is surface defects, grain boundaries, twin boundaries, stacking defaults and free surfaces, that is are most common in 2D type of surface defects. Even volume defects, that is the 3 defects, that is voids or micro cracks are present in that crystalline materials. So this is just depending upon the crystalline size. I said this type of property will affect depending upon the grain size of that materials, nanocrystalline materials. If we are able to change larger size to the grain size to the smaller grain size, so these are the common defects are present and we can eliminate and that materials. Okay. So here's that point defects I said, means if that this is absent, or maybe in this particular point interstitial or substitutional defects, you can say point defects. Another is Schottky defect, Frankel defects. Here either these sodiums that are absent, here point defects, this is absent, means same type of ions or different type of ions may absent in that crystals. So that type of defects 0D. And dislocations, that is called line defect, that is 1D type of defects. So this particular order of arrangements of atoms, that is absent. So when that material was prepared in bulk crystalline materials. So and surface defects, and this is grain surface defects, so that is 2D, grain boundary and twin boundary. So here this is one type of grains and this is grain boundary. So this type of in grain boundary, so that absence or dislocations or particular order of arrangements of atoms that would be absent in that particular materials that we are preparing. Okay. So if you are able to decrease the grain size into nanograins, then this type of dislocations stability we can reduced. Okay. So here just these are the things we have already discussed. So different type of in nanocrystalline materials also, these are the type of defects are present and we can eliminate by changing the grain size of that particular materials. Okay. So here is the twins stacking defects, so voids that is also present. Okay, so these are the various type of defects that presents in nanocrystalline materials, so that we have discussed. So depending upon the preparations of this particular nanocrystalline materials, so if we are able to reduce the grain size, so then so we can eliminate those kind of defects when that materials we are preparing. Okay, so that would be useful for a particular applications where that materials is useful. Thank you. Okay.